Hi everybody. Alright, so instead of meeting today, I am making you this video because I am sick and can't come into campus. I tested positive for COVID, as I mentioned in the last video, which hopefully you got, that was supposed to cover our Tuesday class. So this video is supposed to cover the Thursday class. The material for the Thursday class is the 3.2 and 3.3 homework assignment, where we learn this thing called the fundamental theorem of calculus, and we sort of approach this idea of antiderivatives. Turns out these two things are very closely related, and they work kind of nicely to answer the question that was sort of proposed but not really answered in 3.1. Hopefully you've seen all the videos on this stuff, so this all makes sense to you. What I want to do is both go through the homework assignment but also talk a little bit about this week's quiz. So I think I started talking about this week's quiz in the last video that I made. The quiz will cover 3.1 and this 3.2 and 3.3 stuff. From 3.1, make sure that you can estimate the area underneath the curve by doing left endpoint and right endpoint rectangular approximations. From 3.2 and 3.3, there's two learning objectives that you really want to be comfortable with. The first one is you want to be able to evaluate antiderivatives. So if you see a question like this, for example, it'd be nice if you could answer this question, and I can change the function that you're given in here to change the difficulty level of these antiderivatives. I think there's 3 or 4 of these on the quiz, and the difficulty level varies, but it should be pretty consistent with what you see in this homework assignment. So that's the first of the different learning objectives. The second of the learning objectives is to apply the fundamental theorem of calculus. And what the fundamental theorem of calculus says is that when you're trying to evaluate definite integrals, so not just antiderivatives like we see up here, but definite integrals, so you have numbers in place here of your bounds, all you have to do is take the antiderivative of this function and evaluate it at the upper bound, and then subtract the antiderivative of this function, evaluate it at the lower bound. So for example, if you were asked to evaluate the definite integral from 0 to 45 of, 2 over 45 t plus 3, all you would have to do is find the antiderivative of this function and then evaluate it 0, 45, and take the difference between those two things. And if you're wondering why I use this example, well, it's exactly what we're doing here. All right, so this is a problem that showed up at the end of the last homework assignment where we were supposed to figure out how far did the object travel from 0 to 45. So how much area is there underneath the curve from here to here? And you could do this using the methods of the previous section by recognizing that, hey, look, I got this rectangle right here, and the area of this rectangle, well, it's 45 by 3. So whatever 45 times 3 is equal to, 135, I think, is the area of this rectangle. But then I also have this triangle right here, and the length of the base is 45, and the height is 2. And the area of a triangle is 1/2 the base times the height. So the area of this triangle will be 1/2 45 times 2. In other words, 45. If you take that 45 and the 3 45s down here, I think you end up with 180 as your answer when you add up those two areas. This one was 45 and this one was 135, if I'm remembering all those numbers right. But the point is, or was supposed to be, that you don't have to do it this way anymore. There's a better way to do this problem. The better way to do this problem is to come up with the equation of this line. The equation of this line is 2/45 t plus 3. Wait, where's that come from? It's a straight line, so it's in the form y equals mx plus b. From here, I can tell that b is equal to 3. And then I can look for the slope. It goes up 2 units. Each time it goes to the right by 45 units. So the slope is equal to 2 over 45. Therefore, this is the equation of this line. So if I want to know the area underneath the line, I just evaluate the definite integral from 0 to 45 of 2/45 t plus 3. And to evaluate that, I can use my fundamental theorem of calculus. To use my fundamental theorem of calculus, I need to be able to figure out the antiderivative. So really, these two learning objectives are very closely tied together. So really, you can't apply the fundamental theorem of calculus without being able to evaluate antiderivatives, but I want to write them as two separate learning objectives because they'll be tested separately on the quiz. So there'll be a problem where I ask you to figure out how much area there is underneath the curve, and I ask you to use the fundamental theorem of calculus to figure that out, and you'll go through these steps. And there'll be different problems where I just say, figure out a bunch of antiderivatives, and you'll have to figure those out. And really, if you get the hang of this, you'll see that I'm kind of asking you to do the same thing. Anyways, I've gone this far, I might as well finish this problem. I mean, we know what the answer should be from the methods of the previous section, but maybe we can solve it this way for the methods of this section. The way you'd want to look at this is we need to know the antiderivative, and then we'll evaluate that antiderivative from 0 to 45. Maybe you're at the point where you can just calculate this antiderivative right here, but in case you can't, you can calculate the antiderivative off to the side. Note I'm changing symbols a little bit here. I'm doing so intentionally. The definite integral needs to be evaluated from 0 to 45. To figure out that definite integral, I need the antiderivative right here. A way to write that I'm figuring out the antiderivative is by writing this integral symbol without the values on my endpoints. Anyways, to figure out this antiderivative, what I would do is recognize that I'm taking the antiderivative of a sum of two terms. So I can take the antiderivative of each term individually. This first term has a coefficient of 2/45, so I can pull that 2/45 out in front of the integral symbol. I get the integral of t dt plus the integral of 3 dt. And hopefully these are things we can both figure out. Let's see, the 2/45, I leave that alone because that's not in between my integral symbol. This is t to the first power. So when I take the antiderivative, I have to add 1 to that exponent, so it becomes t squared. But it's not just t squared, because if I was taking the derivative of t squared, I'd get 2t. But I don't want 2t, I just want 1t, so there must be a 1/2 right here. The antiderivative of t is 1/2 t squared, so the antiderivative of 2/45 t is 2/45 times 1/2 t squared. And yeah, I could tack on a plus c, but I'm not going to bother until I figure out the antiderivative of this term. The antiderivative of 3, that's pretty easy. I could pull the 3 out in front, and the antiderivative of 1 is just equal to t. Or I could just say this is 3t, because the derivative of 3t would just be 3. In order for these equal signs to hold, I guess I should put a plus c right here. But for the sake of this problem, I don't need the plus c, because for definite integrals, you don't have to include the constant. This is what's going to go up here. I'm going to say that if I'm evaluating the definite integral from 0 to 45 of 2/45 of t plus 3 dt, what I got to do is take this expression, which simplifies to what? 1/45 t squared plus 3t, and evaluate that from 45 to 0. So the way I evaluate that is I copy exactly what I see here, changing all the t's into 45s. So I get 1/45 times 45 squared plus 3 times 45. And then I figure out that answer and subtract from that what I get when I evaluate this at 0. But a nice thing happens when I evaluate it at 0, right? This turns into a 0, and this turns into a 0, so I'm not really subtracting anything here. What's this equal to? Well, 45 squared, I don't know what that's equal to, but I don't have to figure it out because one of those 45s will cancel with this 45. So 1/45 of 45 squared is just 45. And then from here, I get 3 of these 45s, and then from that I want to subtract 0. So I have 1 of these 45s plus 3 more of these 45s. It sure sounds like I have 4 of these 45s. And 4 45s are the same as 2 90s, which is 180. The same answer that I would have gotten if I added these two up and used the methods of the previous section. At this point, you might argue that the methods of the previous section are a lot easier than what we did here, and they are for this specific example, but the problem is the methods of the previous section only work when the function here is linear, which is very limiting because typically we're not going to have linear functions in there. So that's a lot of talking just on this first homework problem, but I thought I could really introduce all the different terms and go over the learning objectives and how they relate to the quiz by doing this problem and kind of doing it several different ways, using the methods of the previous section and the methods of the new section. If you can understand what I did here and all the different symbols, and even the subtleties, right, how I switched from definite integrals to indefinite integrals. This symbol here just means find the antiderivative, which is different from this symbol, which means figure out the antiderivative and then evaluate it at the two different endpoints. If it helps organize your thoughts, you can think about everything in this little green blob here as kind of side work. All this side work was just to figure out what I write right here, which probably by the time you're taking the quiz, you'll be able to look at this and just tell what the antiderivative is and write that right here. The big takeaway from this first problem is when you're trying to figure out the area underneath the curve, you're evaluating definite integrals. When you're evaluating definite integrals, you're going to use the fundamental theorem of calculus. In order to use the fundamental theorem of calculus, you need to know antiderivatives. So really, this first learning objective of evaluating antiderivatives is super important in order to do the second learning objective. So for that reason, I kind of give you this problem to sort of motivate what you're doing, but then the rest of the homework problems, I focus less on the geometry and I give you the questions more written in a calculus sense. Evaluate the definite integral using antiderivatives, aka the fundamental theorem of calculus. You don't need to draw this picture at all. You don't need to find the area of any rectangles or any triangles. All you need to do is take the antiderivative of this and evaluate it from 3 to 8. Evaluate it at 8 and then subtract what you get when you evaluate it at 3. If it helps, little f of x is equal to 4x plus 9. You first figure out capital F of x, then figure out capital F of 8 minus capital F of 3, and that will be the answer that you write right there. I think from 4x plus 9 you can figure out capital F of x if you watch the video, so I'll leave that part to you. Question 3, a little bit early for a word problem. I think the reason I put this on here is because it's a word problem you've seen before. If I remember right, this was in the previous homework assignment, and this is one that you can figure out with rectangles and triangles, but you don't have to. Now we have our function right here. They use capital P of t. Might make more sense if you write that as lowercase f of t equals 54 plus 2t. Maybe you could figure out capital F of t and then answer the question by figuring out capital F of 6 minus capital F of 0, and that will go right here. If you've done these first few problems, what you'll see is really most of the work, most of the new knowledge that you need happens between step 1 and step 2, right? Figuring out this antiderivative. Here you're just plugging in numbers and subtracting stuff. It's not that hard. Really, it's can you figure out capital F of t, the antiderivative of your function. So since that's the most important thing that you're doing here, there's several problems where that's all you do. Right? Question 4, question 5, question 6, question 7, question 8, question 9. These are all just antiderivative problems, right? I'm going to have you do a bunch of these because I'm going to ask you to do exactly this on your quiz. So on your quiz, there'll definitely be a problem that kind of looks like question 1, where you want to apply the fundamental theorem of calculus to evaluate a definite integral. But there'll also be several on the back, I think there's 3 of them, where you're just evaluating antiderivatives. And when I say just evaluating antiderivatives, think question 4, question 5, 6, 7, 8, and 9. And I chose these questions for the homework to try to give you an idea of what you should expect to see on the quiz. So there's a variety of difficulty that you'll see when you work through these different problems, just like there's a variety of difficulty on the problems that you see on the quiz. Note that on the homework, they already include the plus C for you, so you don't have to remember to write that when you're figuring out these antiderivatives. On the quiz, I don't include it for you, so technically you should include it, but I can tell you, as I'm the person who made the solutions, that I wrote like, hey, if you forgot the plus C, don't worry about it, don't take off any credit. Technically, there should be a plus C on any of these antiderivatives, but if you leave it off, I'm not worried about it. How do you answer these questions? Well, let's see. I bet you could do 4 by yourself. Maybe I'll do 5, and then I'll do 7, and that'll give you a good kind of idea basis of these different problems. For 5, you'll get to the point, just like you are with derivatives right now, where you can look at this and immediately tell what the answer is. It's not a bad idea for the sake of the quiz, and even for the homework early on, to get in the habit of showing a few steps of work. To be like, all right, I can pull the 5 out in front, and then I got to take the antiderivative of x to the 6th power, and then in the other term, I can pull the 4 out in front, and I take the antiderivative of x to the 4th power. You don't have to write this step, but if you're making mistakes and you show this step, it's a lot easier, I can tell you as a grader, to give you partial credit on things like your final exam. So it's not a bad habit to get into. Anyways, this 5 is not in between these symbols, so I do nothing with it. The only antiderivative I need to take is x to the 6th power. Start with x to the 6th power, but think about if you're taking the derivative of something, you have to subtract 1 from the exponent. So instead of being x to the 6th power, I must start out with x to the 7th power, so that when I take the derivative of this, I get this. But you're like, nah, there's a problem. If you take the derivative of x to the 7th, you don't get x to the 6th. You get 7x to the 6th. And you don't want to get 7x to the 6th. You want to get 1x to the 6th. I'm like, don't worry about it. I'll just toss a 1/7 right there. Because now when I take the derivative of this, the 7 and the 1/7 will cancel out, and then I'll subtract 1 from the exponent to produce this 6, and I'll be left with exactly 5x to the 6th power, what I was trying to get over here. Same logic on this next term. I'd leave the 4 alone. I'd think about my x is now going to be x to the 5th power, but not just x to the 5th power, x to the 5th with a 1/5 out in front of it. Could leave your answer like this, but nobody does. Maybe it's a little bit prettier if I write it as 5x to the 7th over 7, maybe, plus 4x to the 5th over 5. Sure, that's one way you could write this answer. This is on par with the difficulty level of the easiest one you'll see on your quiz, for what that's worth. Question 6 is a little bit trickier. However, if you can do question 7, I'm pretty sure you can do question 6. So I'm going to skip 6 and jump straight down to 7 here. The idea for 7 is this problem is not written in a way that's conducive to your different antiderivative rules right now. But what you could do is you could rewrite it. You'd be like, all right, I got to take the antiderivative of this 5x to the 5th. Let's pull the 5 out in front, and I'll worry about the antiderivative of x to the 5th in just a sec. For the next term, I'm going to pull the negative out in front, and I'm going to take the antiderivative of 1 over x. You could rewrite this as x to the negative 1 power if you want, or you can leave it as 1 over x. Either way is fine, and I'll talk about y in just a sec. For this next term, I'm going to pull the negative 6 out in front and have the antiderivative of 1 over x to the 4th power, which I'll write as x to the negative 4th power. It's a lot of algebra going on there, so make sure you can see how this is the same as this over here. Right? This is equal to negative 6 times 1 over x to the 4th. And being able to see that these two things are equal are really handy when you're trying to do these algebraic manipulations. So go from here to here, then recognize negative 6 is a coefficient, so that goes out in front, and then recognize that 1 over x to the 4th is the same as x to the negative 4th power. Finally, for this last term, I could pull the negative 2 out in front of the integral symbol, and then what I would have left is the square root of x, which I'm going to rewrite as x to the 1/2 power, because the square root of x is the same as x to the 1/2 power. I bet if you get this far, you can finish the problem. However, I think I'm going to do it for you, because, I don't know, these videos are short anyways. When I end up editing them, they cut down really short, and I want to help you as much as I can. What we've done is we've changed one hard problem into 4, easier problems, I guess. For this first problem, the 5 gets left alone. The antiderivative of x to the 5th. Think about it like I want to add 1 to the exponent, because when I'm taking derivatives, I subtract 1 from the exponent, but I need a 1/6 out in front so that when I bring this 6 down in front using the power rule, if I'm taking derivatives, I don't end up with 6x to the 5th, but just 1x to the 5th. From this next term, you'll note that I didn't rewrite this as x to the negative 1 power, because I don't need to. And if I wrote it as x to the negative 1 power, you might think that you're supposed to use the power rule. But remember, there's one case where you don't use the power rule. It's when the exponent is negative 1. Because if you tried to use the power rule when the exponent was negative 1, you'd add 1 to that negative 1 and get 0. And you'd be dividing by 0, and things wouldn't work. And that might help you remember that you don't use the power rule here. If you don't use the power rule, what do you use? Well, it's the natural log. Technically, the natural log of the absolute value of x goes in here. Although on the quiz, if you forget the absolute value symbols, I'm not too worried about it. I kind of think about this like a trick question, and it 100% shows up on the quiz. So make sure that you remember this antiderivative is not the power rule and instead uses the natural log. What about this one here? Well, what I think would help is leave the negative 6 alone and then jump to the x. X should not be to the negative 4 power. It should be 1 more than negative 4, which is negative 3. But I can't just change this, because if I'm taking the derivative, the negative 3 would come down in front. So I need 1 divided by that negative 3. This is really ugly looking right now, but that's okay. We'll save that in the next line. For now, leave it all ugly like this. Makes it easier to follow your work. This last one, I leave the negative 2 alone. I add 1 to the exponent. The exponent used to be 1/2, so now it's 3/2. And I want to divide by that 3/2. You can put 1 over 3/2 if you want, or you can put 2/3 here if that's easier for you. I prefer the 2/3 because then I don't get fractions inside fractions, but I'll leave it up to you. This is an acceptable answer the way it's written, but you might want to clean it up a little bit. You might want to make it 5/6 x to the 6th power minus the natural log of the absolute value of x. And then I have a negative and a negative, so that turns positive. And 6 over 3 is 2. So I have plus 2x to the negative 3rd power. And then this negative 2 and this 2 give me negative 4. So I can make it minus 4/3 x to the 3/2 power. Different ways you can rewrite this, but I'd argue that this is plenty simplified enough. This would get you full credit on a quiz, and it's a good way to leave your answer for the homework. I don't think there's anything especially tricky in question 8 that we didn't go over in question 7, so hopefully you can tackle question 8 on your own. Question 9, there's a little trick. I'm not going to do the whole thing for you, but really the trick here is be careful. Don't just take the antiderivative of this and try to multiply it by the antiderivative of this. That won't work. Right? Much like you had a product rule for derivatives, we can't just take antiderivatives of products like this. There's something special that you have to do that you haven't learned yet. So what do? Well, you rewrite this in a form that's conducive to the rules that you have. Right? Rewrite this as the antiderivative of x squared plus x minus 30 dx. Wait, where'd all those numbers come from? I'm just doing FOIL. Right? X times x gives me x squared. Here's 6x, but here's negative 5x. So those net out to give me the positive 1x. And then the 6 times the negative 5 gives me the negative 30. The antiderivative of this is not at all hard to take. It's kind of like what we did way up here in question 5. But I'd argue that question 9 is a lot harder than question 5 because a lot of students wouldn't see that, oh, I should use FOIL to switch this form so that it fits my different rules. So that's just something to be careful of. Question 9 is kind of a trick question. Nothing too special going on with question 10. It should look a lot like what you saw in question 5. We're able to figure out the antiderivative in question 5. Just note in question 10 there's one extra step, right? Find the antiderivative, but then evaluate it at these points and subtract your two answers. Be really careful with parentheses here. Maybe I should just do the problem. When you take this antiderivative, I think what you'll end up with is 7/5 x to the 5th power plus 2/7 x to the 7th power. And if you're not sure that's right, maybe you can check this by taking the derivative of this and making sure that takes you back over to here. But that's not the answer. I need to evaluate that from -2 to +3. So I change all my x's into 3's, and I get 7/5 times 3 to the 5th power plus 2/7 times 3 to the 7th power. And then I have to subtract from that 7/5 times -2, careful with the parentheses, to the 5th power. Although I guess in this case, if you left them off, you'd get lucky and it wouldn't be incorrect. Plus 2/7 times -2 to the 7th power. And you're like, that's exactly what I typed in, and it marked it incorrect. That's because this is incorrect. What's incorrect about this? I'm only subtracting the first term. Because my antiderivative has two terms, I got to be really careful in how I evaluate them. I want to take capital F of 3, that's all this stuff. You don't need the parentheses, it's just meant to illustrate a point. And I want to subtract capital F of -2. So I want to subtract all this stuff. This second set of parentheses are really important. Without this second set of parentheses, it's going to mark your answer incorrect. So be careful there. You can leave your answer as an expression. You don't have to actually figure out what 3 to the 5th power is or 3 to the 7th power. I mean, you can if you want, but you don't have to. I'd leave my answer kind of like this, but be really careful with the parentheses. Nothing too special on question 11. I think that one will go pretty smoothly for you. Figure out the antiderivative. Maybe when you're figuring out the antiderivative, it'll help to rewrite this as x to the -2 power, and then evaluate it at 4 and 6. Figure out your answer. It goes right here. Question 12, same thing. I think you'll find question 12 is sort of similar to question 6. It has that same little trick that we saw with this term that involves natural logs. So that's something to look out for when you get to question 12. A couple of comments. The natural log of e squared is equal to the number 2, and the natural log of 1 is equal to the number of 0. You might remember this from a pre-calculus class, that the natural log of e squared is asking you what power do you have to raise this implied e up to change it into e squared. So since the e that's implied here, squared, is the same as e squared, this is equal to 2. And what power do you have to raise the implied e up to change it into a 1? Well, because e to the 0 power equals 1, the answer is 0. So a quick refresher on logs that you may or may not remember. These are facts that if you know, it's great. If you don't, it's not the end of the world. You actually don't even need these to answer this question, but with these two facts, your answer will simplify really nicely. So if you're interested in simplifying your answer, here's just a couple little hints for you in the simplification. But if you don't want to use these, then just don't simplify in your answer. You're fine. I got a little hint on question 13 as well. Be careful here. You have a quotient of terms, and we don't have any rules for quotients of terms. But maybe you can rewrite this as 6x squared over the square root of x and 5 over the square root of x, and then you can take these antiderivatives individually. You'll notice that you still have division going on here, but maybe if you think about this as x to the 1/2 power, you'll be able to see how this is the same as 6x to the 3/2 power. When you subtract the exponents, maybe you can do something similar with this to write this as 5x to the -1/2 power. And after all this algebra, you'll finally be ready to start some calculus. Right? I haven't done any antiderivatives yet, but at this stage, you can take an antiderivative, and then you can evaluate that antiderivative at your various endpoints to get the answer that you put in right here. So lots of algebra on the front end of this problem because we don't know methods for undoing the quotient rule at this point in our class. At this point, you're done with anything that you might see on the quiz, so the rest is just finishing up the homework. We got 3 more problems. They're all word problems, although I think what you'll see is they're not especially challenging word problems. These word problems are really just asking you to evaluate definite integrals. So they give you the traffic flow as a function, where t is in hours and t equals 0 is 6 a.m. and they want you to figure out how many cars pass through the intersection between 6 a.m., when t is equal to 0, and 9 a.m., well, that must be t equals 3 because that's 3 hours after this. One application of definite integrals is allows you to figure out like the total number of things if you know the rate of flow. What I'm saying is this question in words can be rewritten in symbols as the definite integral from 0 to 3 of 400 plus 700t minus 120t squared dt. All of a sudden it looks a lot like one of these problems, 10, 11, 12, 13, maybe even a little bit easier. So maybe you can evaluate this and that answer goes here. And that's not specific to 14. I think that same thing happens for 15 and 16. We throw some business calculus terms around. It's kind of nice being a business calculus class. We have a marginal cost function. Oh, how cool. Find the total cost of the first 81 units. As you probably guessed, this is just asking you to figure out the definite integral from 0 to 81 of 7 over the square root of x dx. Same logic down here where we have a rate of growth of sales. We want to figure out a formula for the total number of sales in the first t days. I guess this one's actually a little bit interesting. This one's kind of hard. Why don't we make this one extra credit, and I can make a couple of comments for you. The first one is the total number of sales in the first t days is going to be initial sales plus the total kind of change in sales, accumulated sales maybe. So your answer will be something plus something else. The initial sales, which I believe they give you in the problem, and the accumulated sales. To get the accumulated sales, you're going to evaluate a definite integral. If we want the accumulated sales up to the 50th day, we'd go from 0 to 50. But we don't want it up to the 50th day. We want it on the first t days. So we're going to go from 0 to t. I know that seems weird, but don't worry, it's not going to be messed up. What are we taking the definite integral of? Well, the one function that's given in the problem, 45e to the 0.01t dt. This 45 is just a constant, so we can pull it out in front. We got 45 times the definite integral from 0 to t of e to the 0.01t dt. Two problems. First off, you're not used to seeing a t up here. In the past, this has been a number. Don't worry, it changes nothing. Instead of figuring out the antiderivative and evaluating it like, 50 and then 0 and taking the difference between the two, just evaluate it at t and then 0 and take the difference between the two. Change all of the t's in your antiderivative into t's. You won't have to make any change. And then subtract what you get when you change all these t's into zeros. The other comment that I want to make is you don't know the antiderivative of e to the 0.01t. The antiderivative of e to the 0.01t dt is hard. Maybe it'll help you to think about the antiderivative of e to the 2t dt. Maybe if you can answer this question first, which I think I did something similar or maybe exactly this in the videos, that'll allow you to answer this question, and then when you can answer this question, you can finish up this problem. So hopefully that's enough of an outline for you. Again, this problem's extra credit, so if you don't want to mess with it, you don't have to. Your final answer will be the initial sales, which is this 600 right here, plus the accumulated sales, and the accumulated sales will be this definite integral, where we figure out the antiderivative of this function, and then we change all of the variables into t's, zeros, and then find the difference between those two values. That gets us to the end of the homework, so I guess that gets us to the end of this video. Good luck with the quiz. I'll see you guys on Tuesday. Have a good weekend, and let me know if you need anything in the meantime.